Eddy currents. Eddy currents are the currents which develops due to the magnetic field in the material, metric solid materials especially. Metric solid materials in the sense, here we have one concept. These currents will develop always in a form of circuit. See, this is a solid material if you are seeing. In this solid material inside
So,
the, yes,
so I'm not able to hear you clearly because like there's that loud like that noise coming.
okay, 1 minute. It's from there only. You turn off
Uh,
your
I
fan or AC.
I muted myself. So now like the sound is coming like from
Yeah,
your like
okay.
your voice is clear.
Hello, now it is how much it is clear? I'm
Yes, so
speaking, right?
now it's little yeah now it's little better.
Yeah, I'm using the earphones to more clarity. So eddy currents are the currents which develops inside the metallic blocks, which is involved in the magnetic field or inducing magnetic field. So, especially here, due to the inducing magnetic fields inside the metals, there are circular currents will develop like this. This circular currents develops. These circular currents leads to dissipation of energy, electrical energy. So, due to more development of these circular currents, leads to more dissipation of electrical energy. So, we need to avoid this eddy currents, okay, for avoiding the dissipation of energy. So here, first of all, how the eddy currents are produced, whether it is producing or not. These eddy currents also called as Foucault current. What is that? The scientist name? Foucault currents. Okay, since it is circular, we call it as eddy currents. Now I'll tell you a simple concept. I'm using a north and south pole of the two strong magnetic poles to produce the magnetic field. Okay, in this direction, the magnetic field has been put. Now I have used a pivot here, or in any roof I have used, or a stand. For that stand I have connected a metal rod which is moving through this, or a metal strip, let us say, which is moving through this magnetic field, and it is moving to and fro. So while it is moving to and fro, what happens in this coil? It is moving with some angle theta, like a pendulum. It is moving. While it is moving to and fro, front and back to the magnetic field. In this metallic piece, there are some amount of currents are developing. How we understood the currents are developed inside? We understood that initially, whenever we have applied some external force to move this pendulum to the magnetic field, it is moving properly. But later on, after 2-3 attempts, it is coming to the rest, or the motion becomes slower. The motion becomes slower, it is coming to rest. So, what happened here? Due to the magnetic field, here in this currents are developing, the developed current produces the poles which is opposite to the these poles. That means here we studied the Lenz law. What is the Lenz law? Lenz law is nothing but says that the inducing magnetic poles or inducing currents which opposes the uh, magnet or motion of a magnet such that it is produced, such that the cause is produced in it, means the same thing it is happening here. When a metallic piece is moving to and fro motion through this magnetic field, means obviously there we are changing the magnetic field. There is a varying magnetic field is there. Due to varying magnetic field, what happens in this current produces? Due to production of this current or the induced currents produces the magnetic field which are the same poles. For example, this is a metallic piece is moving through this in the sense this is the north pole towards that side, north pole develop. This is the south pole towards this side, south pole only will develop. Due to that, what happens? South pole opposes the motion of the south pole. North pole opposes the motion of the north pole. Therefore, therefore, we understood that inside some of the currents are developed. Okay, those currents we called as eddy currents. This is we can understand by the electromagnetic induction process. Since the motion of the coil or a motion of the metal piece or simple pendulum to this magnetic field is decreasing, that is that phenomena we call as electromagnetic damping. What is that? Electromagnetic damping. Damping. Yesterday we also discussed through the pipe. Through the pipe when we have dropped a coin, the coin also experienced some currents and therefore the opposite magnetic field to this steel pipe. Okay, in that case also we have experienced the damping effect. That is we call as electromagnetic damping. In this case, what happened in the core part of the material, since the currents are developing in a circular path, these currents uh, will produce again some of the magnetic poles or induces some more magnetic fields, which is opposed to the, which is opposite to the change produced in itself. Who has produced the change? The input magnetic field. Who is the input magnetic field? The north south poles which are taken initially. Okay. So this is according to Lenz's law. Here electrical inertia is also acting since by opposing the motion. This effect we call as electromagnetic damping. Of course, this effect if you are using wisely, then it is helpful in the applications. Okay, sir. Here electromagnetic damping is taking place. If it is in a generator or if in other cases, if the same process will continue, there is a so much loss of energy takes place. So how can I avoid this? There is a process to avoid that. Whatever between the north and south poles, I'm using the metallic piece. The metallic piece I'm using now in the form of strips. How I'm using? In the form of strips. Right. With the same strip, if it is moving to and fro through the magnetic field, of course there is a damping effect develops. But since I am using in a form of strips, what happens? The currents which are producing here, the currents, circular currents will not continue. It will break. It will break. So if it is continuous like previously, then more amount of dissipation takes place, more amount of energy dissipation. Okay, or we say it is large amount of energy dissipates in a form of heat. Energy dissipates in the form of heat. But here what happened? Due to breaking the circular currents, the motion of the coil through the magnetic field, the motion of the coil to the magnetic field better than earlier. I'm not telling here there is no electromagnetic damping. Electromagnetic damping is there, but it is reduced by using the strips. So these gaps will not allow to continue further the eddy currents. It will break up. If it is a thick material or thick metal piece like this solid, then in that there are the more amount of circular currents will produce. Right? So due to the circular currents only, more dissipation takes place. Whereas if you are using a form of strips, we can break up the current, then we can reduce the eddy currents. Eddy currents. Okay. So this is the way we can reduce. Now there are some applications on eddy currents. What are the applications? Applications of eddy current. First, magnetic braking in trains. Magnetic braking. Where it is magnetic braking in trains. In trains, what type of trains? Usually, if you see magnetic levitated trains, wherever we are using the strong magnetic fields on the rails while the train is moving. Okay, so these trains are moving because of the effect of strong electromagnetic effects only. Strong electromagnetic effects. So, or magnetic levitation process based. Like in Japan, there is a some bullet trains which works on only magnetic levitation concept by strong electromagnetic effects. Of course, strong electromagnetic effects will come from the strong electric fields also. Now, a train is moving. Train needs to stop. Whenever train gets stopped, the train gets stopped when there is a opposite magnetic field develops. Of course, we are inducing the magnetic field between the fields. For example, see, this is the one rail in the sense on the rail, the train is moving like this. This is a rail. On these rails, this train is moving. It doesn't have like tires and all. Uh, it will move like that way. On the two rails, it is adjusted in such a way that due to the inducing magnetic field or due to the magnetic levitation process, it will move in forward direction. So, in this case, when you have applied the external magnetic field in opposite direction, therefore opposite magnetic field, what it will do? These are the magnetic fields is allowing to move the magnet in forward, train in forward direction. So the train wanted to stop in the sense to apply the magnetic field in opposite direction. So in such case, eddy currents are used. So this eddy currents will develop the induced magnetic field on in opposite direction. Therefore, therefore they are acting as a brakes. They are acting as a brake because this is a train moving in the magnetic field, right? So in such a way, while it is moving in the magnetic field, in opposite direction, if you change, then automatically it acts as a brakes in the magnetic levitated trains. Then same concept is applied. Electromagnetic damping in galvanometers. Electromagnetic damping in galvanometer. We studied galvanometer, what is a galvanometer, what are the effects of the galvanometer, right? In the galvanometer, when electromagnetic damping comes into the picture, we know that when a needle usually it rotates in forward direction when current passes through that, right? Current passes through that. Then suddenly the current passed and it has shown the effect. It has shown the effect. The moment if the current is reduced, whatever the metal piece it is connected or the soft iron core it is connected, in that eddy currents which are developed that acts in opposite direction. So the string or the needle will move in opposite direction within short span of time because the currents which are developing here opposite to the applied magnetic field. Okay, so therefore it comes back. Therefore, in this case, electromagnetic damping effect is acts due to the eddy currents. This is because of a solid material, magnetic material you are using inside the galvanometer as a core part in that. Next, induction furnace. Induction furnace. Induction furnace. What is the use of induction furnace? Induction furnace is used to develop or especially is used to produce high temperature. High temperature in the sense like plasma state needs to exist. Okay, so this plasma state we need to exist in the sense we don't have any particular bowl or metallic things to hold this high temperature range. Okay, so whenever in some laboratory nuclear fusion type of components when they are doing the particles, in such case they'll create this, they develop the inside the magnetic fields, inside some frames, the eddy currents. Okay, the eddy currents produces opposite magnetic field in depth. they develop the plasma state. Okay, or they create the plasma state in between the magnetic fields which are producing in opposite direction. Okay, this is happened with the when high frequency alternating current we are allowing to pass through the coil, then only it is possible. Okay, now next fourth one is electric power meters. Whether you know or don't know, to measure the electric current which is coming from outside to our homes for the domestic usage, this electric power meter which is entering here, it will have meters. Okay, through the meter, how much amount of voltage or current is entering into your home. Okay, usually as per the Indian norms, it is 220 volts for domestic voltage. For the UK, it is around 110 volts for each home. So this much amount of voltage will enter per unit second to each and every domestic home or domestic area. This will be calculated by this electric power meter. What does power meter will do? Power meter it is here in the sense when current wire which is coming inside, it passes through the meter. So we have seen the motor effect in the galvanometer. When current flows through the galvanometer coil, what happens? Automatically the needle moves in the such a way it shows the direction, right? Same way when current passes, here the needle gets deflects according to the flaming left angle but we studied already. The deflected needle, the deflected needle, okay, what it shows? It shows that nothing but it is showing how much amount of current is entering. Depends on that the coil induces magnetic field there. This induced magnetic field opposite to the entering current. So the induced magnetic field again it produces the current. That current will be calculated here. That is shows in a form of rotation effect. The needle rotates like this. Actually, in olden days, the meters are like this disc. This disc will rotate. This disc will rotate. While it is rotating, how much it rotates depends on the rotation. You will find a meter. There are number-wise meters. For example, if you see speedometer in the vehicles, like 5, 2, 3, 4, 6, like this. Only first it will move 5 in the sense this is it will go up, it is 6. When 6 comes, here 7. Like this it will rotate, like this rotation will be. So for each and every digit has the rotation. This rotation takes place because of the eddy currents only. Because the direct current which is passing through the meter, so due to the direct current in the coil, there is some motion we produce. The motion is producing by the induced field or induced currents in the metallic piece or coil. Okay, so due to that only we can find the rotation of these members in that. Even in speedometer also, how much faster you move, that much rotation you can find in the speedometer on the bikes. Nowadays digital meters has come, of course the technology has changed. Earlier first to see this effect, we found this motor concept only in that also event to rotate. Due to this rotation effect or due to motion produced due to opposing field, then that we call here usage of eddy currents, we can say, automatically. This eddy currents, where it has produced, how the disk has rotated, because the eddy current produced in a coil, therefore the disk has rotated here. Okay, of course, per unit second I said 220 volts in the sense that will be entered in a form of AC signal, like we know AC sinusoidal waveform. We have seen yesterday's class also, right? So this is in AC form which is entering. Whenever positive enters and whenever negative enters, depends on that in the coil. There is a fields induces. Depends on the inducing fields. Then opposite currents develops. The opposite current which develop is called as eddy currents. That eddy currents are produces or motion in the meters. Okay, so how much amount of current enters depends on that the power meters will work. These power meters are analog meters actually. Earlier it was analog meters only we are having. Nowadays technology has come and changed lot of things. So digitally we are getting everything. Even in the car also speedometers you are finding digital meters. The whole car if you see you will find this type of meters which rotates, which shows the speed and okay. These all we can say applications of eddy currents. Not only here, of course, in the case of transformers also eddy currents will produce that we'll discuss in the next chapter. But there, due to this eddy current, there are some losses. Here we discuss about the usage. What is that? Magnetic braking in trains. Magnetic braking is the currents which is developed in opposite direction by the inducing fields. We can able to stop the trains which are working on the magnetic levitation process. Next, electromagnetic damping in galvanometer, which reduces or which produces opposing torque also I can say here. And induction furnace especially like in nuclear labs or wherever in chemical labs, wherever we need a high amount of temperature material to hold. To holding purpose, we will create by using the coils some amount of electromagnetic field. In that electromagnetic field, we can hold a high temperature like plasma source. Next, electric power meters, still now which we have discussed, which eddy currents are induces in the disk. Therefore, uh, sinusoidally, whatever the currents are entering, that will be measured. Next, after this eddy currents, in this lesson, we have most important topic, which is called as inductance. What is that? Inductance.